Welcome to the wacky world of quantum physics. It's a place where particles throw logic out the window, existing in multiple places at once and changing outcomes just because we're watching. It's like the universe's way of saying surprise. These mind-bending concepts make quantum physics both fascinating and, let's be honest, a bit of a head-scratcher. But here's the kicker. This bizarre realm isn't just for sci-fi movies or theoretical physicists. Quantum mechanics is the unsung hero behind much of our modern technology. It's like the backstage crew, making sure the show goes on without a hitch, even if we don't see them. Take your smartphone, for instance. It's not just a device for cat videos and selfies, it's a quantum marvel. The lasers in your CD player? Yep, quantum mechanics at work. These tiny particles, electrons and photons, are the real MVPs, following rules that make our everyday gadgets possible. And it doesn't stop there. Quantum mechanics is like the universe's secret sauce, influencing everything from the stars in the sky to the molecules in our bodies. It's the ultimate multitasker, governing interactions at the smallest scales and shaping the cosmos. Think about the sun, our very own cosmic power plant. This giant ball of plasma is constantly churning out energy thanks to nuclear fusion. It's like the sun's way of saying, "You're welcome, Earth." This fusion process is powered by quantum tunneling, where particles pull off a Houdini act, passing through barriers that classical physics says they shouldn't. Without quantum tunneling, the sun would be a dud and we'd be in big trouble. No light, no warmth, no life as we know it. So next time you enjoy a sunny day, give a nod to quantum physics for making it possible. This stellar magic trick isn't just for the sun. Quantum tunneling is also behind many of our coolest technologies, like the scanning tunneling microscope. This nifty device lets us see surfaces at the atomic level, making us feel like giants peering into a tiny world. And let's not forget transistors, the unsung heroes of our digital age. These tiny devices are the building blocks of computers and smartphones, making sure everything runs smoothly. Transistors rely on the quantum nature of electrons, especially their ability to be in multiple states at once. A concept called superposition. It's like having your cake and eating it too. This superpower is what makes quantum computing possible, promising to revolutionize technology with its mind-blowing computational power. So, there you have it, a glimpse into how quantum physics shapes our world. From the tiniest particles to the vastness of the universe, it's the ultimate game changer. And the best part? We're just getting started. In the next sections, we'll dive deeper into the quirks and wonders of quantum physics. We'll explore how particles can be entangled across vast distances and how quantum computing could change everything. So buckle up and get ready for a wild ride through the quantum realm, where the rules of reality are rewritten and the possibilities are endless. One of the most mind-boggling aspects of quantum mechanics is the concept of entanglement, a phenomenon Einstein famously dubbed spooky action at a distance. Imagine two particles linked in a way that defies our classical intuition. They are connected not physically but through some invisible quantum thread. Here's the spooky part. Measure a property of one particle, say its spin, and instantly you know the spin of the other particle no matter how far apart they are. This instantaneous correlation, seemingly violating the cosmic speed limit of light, puzzled even the greatest minds for decades. Enter Bell's theorem, a brilliant piece of mathematical reasoning that settled the debate. It showed that the predictions of quantum mechanics, including entanglement, were incompatible with any theory that relied on local realism. The intuitive notion that objects can only be influenced by their immediate surroundings. Bell's theorem, experimentally confirmed numerous times, shattered our classical prejudices, proving that the universe is fundamentally non-local. This means that objects can be correlated in ways that transcend space and time, a concept that continues to challenge our understanding of reality and fuel exciting research in quantum computing and communication. Quantum field theory, our best framework for understanding the quantum world, ran into a rather embarrassing problem early on. It was plagued by infinities. These infinities cropped up in the most inconvenient places, making it nearly impossible to get meaningful results from the theory. When calculating certain physical quantities, like the mass and charge of particles, the equations would spit out nonsensical infinite values. this was a huge problem because, in the real world, these quantities are finite and measurable. Talk about a cosmic headache. Imagine spending countless hours working on complex equations only to end up with infinities that make no physical sense. Thankfully, physicists are a resourceful bunch. They didn't give up in the face of these daunting infinities. They devised a clever mathematical trick called renormalization to deal with these pesky infinities. Renormalization is a process that allows physicists to redefine certain quantities in a way that makes the infinities disappear. Think of it like this. Imagine you're trying to measure the length of a coastline on a map. At first glance, it seems straightforward, but the closer you look, the more complicated it becomes. The closer you zoom in, the more jagged the coastline appears, leading to a longer and longer measured length, potentially even approaching infinity. This is similar to the problem physicists faced with their equations. Renormalization, in a way, is like choosing a specific scale to measure the coastline, ignoring the infinitesimally small details that don't significantly impact the overall measurement. By doing this, physicists can focus on the big picture and get meaningful results. It's a way of systematically cancelling out the infinities, allowing physicists to extract meaningful, finite values from the theory. This process involves redefining certain parameters in the equation so that the infinities are effectively removed. While renormalization might seem like a mathematical sleight of hand, it has proven incredibly successful in making accurate predictions, solidifying its place as a cornerstone of quantum field theory. It has allowed physicists to make sense of the quantum world and make predictions that have been confirmed by experiments. It's a testament to the ingenuity of physicists in taming the wild infinities of the quantum world. Without renormalization, our understanding of quantum field theory would be incomplete, and many of the technological advancements we take for granted today might not have been possible. Renormalization has not only provided a solution to the problem of infinities, but has also opened up new avenues of research and discovery. It continues to be a vital tool in the ongoing quest to understand the fundamental nature of reality. So the next time you marvel at the wonders of modern technology or the mysteries of the quantum world, remember the unsung hero of renormalization, quietly working behind the scenes to make it all possible. In the quantum world, particles are notorious for their rebellious behavior, defying our classical intuitions about how things should move. Unlike the predictable paths of planets orbiting the sun or a ball rolling down a hill, quantum particles dance to their own tune, often leaving us baffled. Instead of following a single, well-defined path, they seem to explore all possible paths simultaneously, like a quantum tourist with an insatiable wanderlust. Imagine trying to trace the steps of someone who decides to take every possible route to their destination at the same time. This is where Richard Feynman, a physicist known for his playful genius, entered the scene with his path-integral formulation of quantum mechanics. Feynman, with his knack for thinking outside the box, revolutionized our understanding of particle behavior. Imagine a particle wanting to travel from point A to point B. In our everyday world, it would take the most direct route, like a car driving straight down a highway. In the quantum realm, it doesn't simply choose the shortest route. Instead, it considers all possible paths, even the ones that seem utterly nonsensical. Instead, it considers all possible paths, even the most absurd ones, like taking a detour to the Andromeda galaxy and back. This might sound like science fiction, but in the quantum world, such possibilities are part of the reality. Feynman assigned a probability amplitude to each path, a complex number that encodes information about how likely the particle is to take that particular route. These amplitudes are not just simple probabilities, they carry phase information, which is crucial in the quantum realm. The final probability of the particle arriving at point B is then determined by summing up the contributions from all possible paths, taking into account their amplitudes and phases. This summing process, known as path integration, is a cornerstone of Feynman's formulation. This approach, while seemingly convoluted, has proven incredibly powerful in making predictions about quantum phenomena. It allows physicists to calculate the likelihood of various outcomes with remarkable precision. It's like understanding the behavior of a crowd by considering the individual movements of every single person, even if they're zigzagging seemingly randomly. Each person's path contributes to the overall pattern, just as each possible path of a particle contributes to its final behavior. Feynman's path integral formulation provides a beautiful and elegant framework for understanding the quantum world's penchant for exploring all possibilities. It captures the essence of quantum mechanics, where uncertainty and probability reign supreme, and where every possible path, no matter how bizarre, plays a role in the grand tapestry of the universe.